Okay, hey folks, we're getting into this third module. This is specifically on translational motion. So you can see here, if you're following along in the book, this is topic 7D. So let's get into it. So in this first learning goal, we're going to talk about solving the very famous particle in a box problem. And so this will, of course, be, for now, one dimension and time independent. So let's do it. Okay, so this is a very famous problem in quantum mechanics, and we'll see that there's a lot of really cool real-world applications of this. So we first start by putting a particle in a box. There it is. And so this particle that we're talking about for now is an electron. Of course, we could make that a proton or something like that if we want. For now, we're going to deal with an electron. And if we look at the boundary conditions, this box has length of 0 to L. Inside the box, potential energy is 0. Outside of the box, the potential energy is infinite. So we can use everything that we've collected thus far. We have our Schrodinger equation, plugging in our kinetic energy operator, right? Kinetic energy operator, because the potential energy inside the box is 0, so we've dropped the potential term. And we learned from last time we can get a general solution for this wave function that looks something like this. And we're going to play with both solutions, the sines and cosines, as well as the exponentials. And also recall we got an energy solution from this from rearranging the wave number solution. And if you recall, the wave number solution went k equals 2me all over h bar squared and all square root. Okay, so what we want to do now is solve this more general solution for a specific solution with our exact boundary conditions of this particle in a box problem. So here is what we know and what we can say about our boundary conditions. So like I said, the potential is infinite at x less than or equal to 0 and x greater than or equal to L. The potential is 0 inside the box, which will be the following, right? Between 0 and L, potential energy is 0. And what this means then is if we look at the value of psi at x equals 0, it must be 0 due to this infinite potential. And similarly, if we look at the value of psi at x equals L, this also must be 0. So right away, we can start to play with this idea here. If I look at sine of 0, or sine where x equals 0 of the following equation, right? I'm going to have a c sine, and of course, k times 0 is 0, plus a d cosine of 0. So now I've got this handy guide right here that's got a sine function for me. And we can see that sine at x equals 0 is 0. So that just drops out to 0, which is looking good so far. However, the cosine of 0 equals 1. So that doesn't work for our boundary condition. So what we can conclude in this problem is that this d term has to be 0 for this specific problem. So now we can rewrite that and say psi of x equals c sine kx. And we've completely dropped off that cosine term because we know that it has to be 0 at x equals 0. And further, we can also say that at x equals L, psi equals c times sine of kl, and that also has to equal 0. So we already know that this expression equals 0 at x equals 0, so that's all good. So what we can conclude here then is c cannot equal 0 because then we don't have a wave function at all. So now what we have to do is find a condition in which the sign of KL equals 0. And so that means KL is going to have to be equal to something that gives us sign equaling 0. And so what we might notice here is at integers of pi, our sign function will, in fact, equal 0. So we will say then that KL must equal n times pi, where n is going to be an integer 1, 2, 3, 4, 5, 6, etc., right? So that when we have that condition now, we will always have sign equals 0 when x equals L, right? With this notion that k times L equals n times pi. Or certainly we could rearrange that and just say k equals n pi over L. So this is going to get us this condition for the boundary conditions. And certainly, we also have to remember that k, it still equals that wave number solution, right? It still equals 2me over h bar squared, all square root. So this equation is also going to give us another way of solving for the energy inside this box. And as we can see, we could do just some simple algebraic manipulation from there. And I'll just write that out really quickly. I've already done the algebra for us. So I'll write that, oops, let's see, that was a weird little line. So E sub n, so that typically means E as a function of this number n. And if I do the algebra here, we end up with n squared over h squared. So the pi from h bar goes away, all over 8 ml squared, where n still equals 1, 2, 3, and 4, etc. And we might be wondering, what is this n thing? Well, I'm going to foreshadow just a little bit here, and we will note that n is what we are going to call a quantum number. And yes, in fact, this one is the principal quantum number n that you learned about in general chemistry. So we're going to talk about this n thing in more detail as we go. And so the final thing that we need to do for this problem is, of course, normalize it. So here we have the solution we came up with based on our boundary conditions, the c sine n pi x over L, right? Where, remember, n is this integer, 1, 2, 3, 4, etc. So now to normalize this thing, we're going to say the following. We're going to say c squared, because we recognize now that's our normalization constant. And we have to normalize this thing over the appropriate boundary conditions from 0 to L. And of course, we know that that's going to be the square modulus of psi of x dx, and that all equals 1. Well, hopefully this looks familiar because we did this problem in our lecture activity. So I'll just kind of go through the result quickly here since we already looked at this. So setting up our square modulus, we know that we can just simply take sine squared because there's no imaginary or complex numbers in there. So n pi x over L dx, and that all equals 1. And so recall now the integral of this, so the definite integral of sine squared of n pi x over L evaluated from 0 to L. So if you recall, that equals L over 2, that entire thing, the integral. And then we still have the c squared, and that all equals 1. So doing some quick algebra here, we can see that c equals the root of 2 over L. Thus, our particle in the box wave function is given as the following. I'm going to call it psi of n, noting that we have that quantum number now. And that all equals root 2 over L sine of n pi x over L. Let's button. Let's see. The undo button. There it is. Okay, beautiful. N pi x over L. And this is only for x between 0 and L, right? Remember, that was our boundary condition. Okay, more on this solution in the coming videos.